Continuing with period 2, we now move on to the 2p atomic orbitals. The 2p orbitals are interesting because they can combine in two different ways. First, we will look at end-to-end overlap of the 2p atomic orbitals, and this traditionally occurs along the z direction or z-axis. Now, just as with our s orbitals, our 2p atomic orbitals can combine either constructively, as shown here for the bonding MO that results from constructive interference of the 2pz atomic orbitals, or destructively, as shown above, which shows the antibonding molecular orbital that results from destructive interference of the 2pz atomic orbitals. The notation for the bonding and antibonding MOs is 3 sigma g, and 3 because it is the third lowest energy sigma molecular orbital. And the antibonding MO is denoted 3 sigma u star, and this is because this is the third lowest energy sigma antibonding molecular orbital. In this case, the bonding MO is given the parity G because as we move from plus x plus y plus z to minus x minus y minus z, we notice that the phase stays the same, moving from blue to blue, and therefore the symmetry of the orbital is grada, or G. For the antibonding MO, as we move from plus x plus y plus z to minus x minus y minus z, we notice that the phase changes from red to blue, and therefore the symmetry of the antibonding molecular orbital is ungrada, or U. Now, the other way that the 2p atomic orbitals can combine is side to side, and the results for side-to-side overlap of the 2p orbitals is shown here. Again, they can combine both constructively, as represented by the bonding molecular orbital shown here, or destructively, as represented by the antibonding molecular orbital shown above. Here you can see that in the case of the antibonding molecular orbital, there's a nodal plane lying between the two nuclei, and that nodal plane is represented by the dashed line. Now, of course, there's another set of orbitals located along the y-axis, and these orbitals are exactly the same as the 2px atomic orbitals, with the difference that they are rotated 90 degrees. And so the bonding and antibonding orbitals that result from the 2py atomic orbitals are identical, and they're just rotated 90 degrees. Now, the energies of these two orbitals are the same, and therefore the bonding MOs are both labeled 1 pi u. Okay? Pi because they are side-to-side overlap, which creates a pi bond. 1 because they're lowest energy pi molecular orbitals. And it's given the parity symbol U because as we move from plus x plus y plus z to minus x minus y minus z, we notice that the phase changes from blue to red. And therefore, it's given the parity ungrada, or U. In the case of the antibonding MOs, it's given the parity symbol G, or grada, because as we move from plus x plus y plus z to minus I x minus y minus z, the phase stays the same. In this case, moves from red to red. And therefore, the antibonding MO has the symbol symmetry G, or ungrada. Right? And again, it's given a 1 enter in front of the pi because it's the lowest energy pi star antibonding molecular orbital. Putting everything together gives us the molecular orbital diagram for O2, F2, and Ne2, which are all located in period 2 of the periodic table. Looking at the atomic orbitals first, we see that the 2s atomic orbitals are the lowest energy atomic orbitals, and the 2p atomic orbitals are higher in energy than the 2s atomic orbitals, as we would expect. The bonding molecular orbital that results from constructive interference of the 2s atomic orbitals is the 2 sigma g bonding MO, which looks like this. And the antibonding MO that results from destructive interference of the 2s atomic orbitals is the 2 sigma u star antibonding MO, which looks like this. Next, we have the bonding molecular orbitals that results from combination of the 2p atomic orbitals. The 3 sigma g bonding MO is shown here and looks like this. This is the lowest energy bonding molecular orbital. It's lower in energy than the pi molecular orbitals because we have much better overlap with sigma bonding than we do with pi bonding, and therefore the 3 sigma G bonding molecular orbital stabilizes the system a lot. However, as a consequence, its corresponding 3 sigma U star antibonding molecular orbital destabilizes the system a lot and is therefore the highest energy antibonding molecular orbital. Next lowest in energy, we have the bonding molecular orbital that results from constructive interference by pi overlap of the 2p atomic orbitals, or side-to-side overlap. And this is given the symbol 1 pi u, pi representing pi bonding, and u representing 1 representing the lowest energy pi bonding molecular orbital. And because the 1 pi u bonding molecular orbitals stabilizes the system a little bit, its corresponding antibonding 1 pi g star antibonding MOs destabilizes the system a little bit. And the representation of the 1 pi g star antibonding MOs are shown here. You'll notice that the 1 pi u bonding MOs actually have 2 molecular orbitals that have the same energy, or in other words, are degenerate. The only difference between the two 1 pi u bonding molecular orbitals is that they are rotated 90 degrees with respect to each other. Similarly, you'll notice we have two 1 pi g star antibonding molecular orbitals that also have the same energy and are degenerate. And the only difference between the 1 pi g star antibonding molecular orbitals is that they also are rotated 90 degrees with respect to one another. So this represents the complete molecular orbital diagram for oxygen, fluorine, and neon, which are all located in period 2.